We're going to go over AP Calculus topic 2.4. As I mentioned in the previous lesson, recognizing that a function's derivative is also a function helps us understand how the two behaviors are related. So let's connect differentiability and continuity. Previously, we illustrated the derivative as the slope of the tangent line going through some point, C, f of c. And to get the slope of that tangent line, we took the limit of the slopes of the secant lines as delta x approached 0. So I'm going to copy the same thing over. Now instead of labeling this point as adding a small nudge in that direction and in that direction, we're just going to relabel it with a point close to C. We'll just call this point x. And we'll relabel f of c plus delta x to just f of x. We get the same concept, except this time we're going to consider limit as x approaches c. If we do that, we get another common way to write the limit form of the derivative. It goes like this. Again, the concept is the same, except instead of delta x approaching 0, we have x approaching c. This limit form of the derivative is helpful in teaching the relationship between differentiability and continuity, which is what this lesson is about. The function is said to be differentiable at c if the limit exists and both the limit from the left and the right are equal. These one-sided limits are called the derivatives from the left and from the right. Let's illustrate with a few examples. Can you recall what the greatest integer function looks like and draw a rough sketch of the graph? The greatest integer function is not continuous at x equals 0. In fact, it's not continuous at any integer, so it's not differentiable at x equals 0. Although it's true that if a function is differentiable at a point, then it's continuous at that point. The converse is not true. Consider the function the absolute value of x minus 2. This function is continuous at x equals 2. But what would you say the derivative is at x equals 2? When we approach 2 from the left side, this is always going to be negative. Absolute value is always going to be positive. So it's going to be negative 1 is the limit. As we approach 2 from the right side, x is larger than 2, so that's positive. Absolute value is positive, so the limit is 1. Here's what that graph looks like. It's the absolute value graph shifted over 2 to the right. Notice that f is continuous at x equals 2, but the one-sided limits, in other words the derivative from the left and the right, are not equal. You can draw more than one tangent line at that point. Therefore, the graph of f does not have a tangent line at 2, 0. F is not differentiable at x equals 2. Let's take a look at one more example, the cube root of x, which can be written this way. What is the slope of the tangent line as x approaches 0? Let's plug in 0 into our definition of limit. Applying the definition to our function, we get 0 to any power 0. We can rewrite x as x to the 1. The larger exponent is in the denominator. So let's move this guy downstairs. Since these both share a common base, when we multiply them, we can add the exponents. As x approaches 0, this number gets larger and larger. The limit is infinite, so we can conclude that the tangent line is vertical at x equals 0. So even though the function is continuous at x equals 0, it's not differentiable. So recapping the lesson, we saw through examples that a function is not differentiable at a point if it's not continuous, or has a sharp turn, or has a vertical tangent line.